Okay, and I haven't really looked at homework 3. That was the multilateralization with yarn type of stuff. So yeah, that was actually kind of just for fun or torture, depending upon how you like to deal with stuff like that. But I've started looking at homework 4, and we will also have an assignment today, as I previewed last week, that will walk you through a design using FMCW radars. And so we'll pick up the lecture where we left off, and then we'll cover cameras and LiDAR real briefly, and then and ultrasonic sensors, and also then we'll dive into machine learning. And along the way, we're going to pick up a little bit of Python skills. So we'll talk a little bit more about that when we get to that part. So let me go ahead and start presenting. Okay. I think we had covered distance with FMCW radars. Recall that these are, when we say FM, that's standing for frequency modulated, kind of a fancy way of saying it's transmitted using a linear chirp, where the frequency varies linearly with respect to time. Right? And we transmit out a chirp, and that energy reflects off of objects out there in front of the antenna somewhere, and reflects back according to its radar cross section, which is a function of its geometry and the conductivity and other material parameters that might make an electromagnetic wave reflect. That's really details in your applied electromagnetics courses, but so we won't go into that type of thing. But yeah, it's going to reflect particularly off of metal objects and come back. Some of that energy comes back to the receiver, and we receive that, but there's a delay that we represent as tau here. And that turns out that the reflected signal, of course, has that same chirp behavior. And if we measure the frequency difference at any time during this overlap of the transmitted pulse and a received pulse, we'll get a signal that has this time duration that's equivalent to the overlap, and at a frequency that is directly related to the distance through the slope of this line and the time that it takes for the signal to travel out there and back. So we've got this distance here, a function of the speed of light, c, the frequency of this IF signal, the slope of the chirp itself, and then a factor of 2 to account for that. Really, we're not looking for the round trip distance. We're looking for the one-way distance, but the measurement is a round trip measurement. Right? So we looked at, there's issues about the resolution of being able to resolve these signals, and that's related to FFT or Fourier transform, discrete Fourier transform concepts and that type of thing, right? And so we end up with some equations here. We looked at resolution and also the max distance. Then we started looking at velocity, and we learned that we can measure phase and we can get a lot of sensitivity out of the phase that really isn't there in this frequency that's related to the slope, that's related to the time, that's related to the distance type thing, right? So we can look at the phase and find that it's very sensitive to the distance. And as it turns out, you can do things like even monitor heartbeats in someone's chest by using an FMCW type radar. They're used in industrial applications quite a bit to monitor vibrations. So there is an ambiguity, though. So we need to worry about, if you go a wavelength, then you've gone 360 degrees and you end up with some ambiguity when you look at how the signal evolves in terms of phase as it travels out there and back, is going through, I'll use an engineering term, bazillions of phase revolutions. And so what we have to remove that ambiguity. So we're really looking at what is this velocity within that one cycle, right? So we end up with some equations of this, so we can relate the change in phase by sending two pulses right after one another and measure the phase difference between the two, and that translates into a incremental distance. But if we know the time, now we know the distance divided by the time gives us velocity, right? So here's that ambiguity issue. And so that sets up a maximum phase that we're able to look at. So we don't want that phase wrapping during or wrapping more than a cycle during that time interval. Right? So we can transmit a whole frame of these EECE space chirps and ultimately perform a Doppler FFT. So now this is our second FFT, and I've got this horribly crude diagram here where we're sending out pulses and gathering data in time, doing an FFT that gives us data in the spectral domain, and we can kind of load up this matrix one after another after we've done n transmissions. So we have n rows of these things. And now wherever we see a target, so there has to be some like peak detection or thresholding or something, some algorithm to determine where there might be energy of interest. And then for that distance offset, that's represented in this X direction, then we can take one of those offsets and now look down that whole column and do an FFT there. That's that Doppler spectrum. And now we can calculate the velocities by looking for peaks in that spectrum. Now, notice that this row here might have lots of points. This column here is probably going to have much fewer points to it. So you'll get a chance to get your hands on that type of thing when you go through the homework assignment. So then we started, I think this is near where we left off, and we decided, okay, we've got distance and we've got velocity, but what about angle? What about bearing? So we decided, let's put a number of receive antennas out here. We'll start with 2, and we will see if we can get some bearing information out of that, or angle of arrival. Now, if you've studied any antenna theory, this is going to look maybe familiar to you. So this would be kind of an antenna array, or maybe you've done some ultrasonics work with arrays or that type of thing. So same type of concepts show up here. We're going to take a transmit antenna. In this simple case, we're going to just use one transmit antenna. We're going to transmit a signal. It's going to hit off of some target, reflect back. But there's going to be some slight distance difference between the signal arriving at this receive antenna versus this receive antenna. And you do a little geometry, a little trigonometry, and if you know this distance here, then you can kind of figure out what this delta D distance here is. But the idea here is that the phase at each antenna will vary as a change in path distance. If this bicyclist is over here, then you're going to have much more of a similar type of time of arrival. This delta D is going to be very small. If he's way over here, then that delta D is going to be larger. Right? So let's look at that in a little bit more detail. I have drawn a lot of this information from some TI, Texas Instrument application notes, and some videos, YouTube videos, and I believe I've linked those on Moodle. But I've changed the notation a little bit. The guy that did the videos uses D here also to represent this spacing. But I find that confusing because we've already used D as this distance out to the target or object. So I'm using L, and kind of another just nomenclature that's somewhat common in array type of systems here. So really here I drew this target pretty close, and these angles, they're not realistic, right? So in reality, this thing is pretty far away compared to these spacings. So these lines look parallel, right? In the extreme where that target or object is way in the distance, instead of them looking angled like this, they're going to look pretty parallel. So now our geometry makes a little bit more sense, right? So now this is truly a right angle here. And if we go from here at this point where this antenna is intersecting the energy of this electromagnetic wave, and we have a spacing here that we'll call L, and we'll note that there's an angle, a theta. That theta is related to the angle that the object or these signals or waves are coming at relative to this normal. Okay, it's really kind of the normal to the line connecting these antennas, right? So this dot dashed line is normal to this line that connects these antennas, and so this theta is relative to that angle there. If you remember some of those geometry proofs you did in high school, then you'll see that this angle is the same as this angle here. And again, using our trig, knowing that we're going to draw that as a right triangle. And we know this L, that's going to be specified as going to be a physical distance, right? And so now we can calculate this delta L as L times the sine of theta. So now this will ultimately give us this phase angle, again, similar to our velocity derivations where we're going to look at what is the phase of the signal in this antenna relative to this antenna, right? So they're intercepting the same signal, but this one's traveled this incrementally small distance farther, right? And that is going to be represented by this 2 pi L, or the L times the sine of theta. And we know that a signal is going to go through a phase transition. It's going to go through 2 pi radians per wavelength. So this ends up being kind of a fraction of that. So we can look at the phase relative to this. And now we can just solve for theta, right? Now, a couple of interesting things here. In particular, note that this is non-linear. We've got this inverse sine here. We've got a sine theta up there. We didn't have that in the angle, in the velocity measurement system, right? Where we're relating phase to velocity. But here, with this angle of arrival, now we've introduced this nonlinearity. And what we can conclude here is that, I'm just going to kind of state it, but the measurement is going to be more accurate when theta is near zero, where the sensitivity is high. When we get out here, it's going to be a little bit harder to measure the distance. And you can look and see how the sine is going to behave relative to this angle. And you'll see that, we're going to get good results out here, out to the left or right, where theta is closer to plus or minus pi over 2 or plus or minus 90 degrees. We're gonna struggle to get good results. All right, so but now we have a technique to determine the angle of arrival. But just like in the previous case with the velocity, that's all nice and simple when there's just one target. But when we have multiple objects out there, we kind of lose, we don't have a means of separating out that data. We're going to look at that in a little bit if it's not already clear to you. So we want to be able to separate targets at the same distance and velocity for reasons similar to the velocity. Recall that with velocity, we built a frame of repeated chirps and performed a fast Fourier transform over, and again, fast Fourier is just an algorithm to efficiently calculate the discrete Fourier transform, but over the frame to isolate phasors rotating at different rates. All right, we briefly kind of mentioned this kind of a hand wavy way last week. Didn't review it earlier, but we're going to look at this. So here we build a frame, but now instead of from multiple chirps, repeated chirps, we're going to do it from multiple antennas. So here, let's take a look at this. So here we've got our transmit antenna represented here. And we've got a couple of different targets out there, objects that are reflecting. Now we have these L antennas. So previous slides, we had just 2 receiving antennas. Now we're going to expand that. So if we look at this, if these guys are all at the same range, we're going to get something that and also they're traveling at the same velocity. How do we discriminate them, right? So they're both going to show up at some location in this velocity versus range graph, right? But each is associated with a phasor, and this phasor is going to rotate at a rate that's relative, that's related to its bearing with respect to these antennas. So if we just looked at this pair of antennas, we might have this type of relationship. But the phases of both of these are going to sum between antenna 1 and antenna 2, and we're not going to be able to discriminate them. But if we continue to add some number of L antennas, capital L now, and then we're going to see that the signals at each one of these antennas is going to combine in a different way because their phasers are rotating at different rates. And don't try to read in too much to these particular positions of these phasers. Just note that as if the signal's over here, then as you look at the signal from antenna 1, 2, 3L here, this phaser of this blue one might be rotating, well, if let's say blue's over here and red's over here, then we're going to be rotating in one direction at one rate with the blue phaser, and the other direction and the other rate at a different rate with the red phaser. So even though in each of these plots, velocity versus range plots, they show up in the same location, we start to see how there's some information encoded in these L antennas. So again, we're going to do an FFT, a Fourier transform on this data. Now, so the first one was the range FFT. Then we did the Doppler FFT to get the velocity. Now we're doing an angle FFT. So we're going to gather this data again out of all these different locations, right? So first one we did along this range axis. The other one we did along this column. Now we're going to build this up using the same location and velocity combination, but we're going to build that into a vector and then do an FFT on that. So then, okay, horribly crude drawing, I'm sorry, but you will see, I'm not going to do much more derivation than this, but you're going to see that these guys are going to exist at different frequencies within this angle FFT domain, right? So, and we're calling them frequencies because it's related to how fast and which direction these phasers are moving in. But it's really the angle that we're looking at. All right, so now we can relate these frequencies to our bearing. So we'll do this angle FFT. We'll look for peaks. Again, you might actually look for a peak as you go through this array. You might have some sort of like thresholding operation and then just try to zero in on that peak, looking for a inflection point where your slope changes from positive to negative, or some other peak detection type of algorithm, and identify peaks of interest, and then where that bin is, that's going to be associated with certain omega 1 or omega 2 or omega whatever, right? And we plug each of those into this equation, and we should get a bearing associated with that. Now, these are all spaced at L, lowercase l increments here. All right, so we can do a little bit of work here in looking at now what is our ability to resolve two targets at small angles, right? So we're going to assume we've got one here at this angle and another one here at this bearing from the targets, right? And we're looking at what is that phase, and can we, or the frequency that's showing up in that angle FFT, and can we really discriminate those? Well, looking at this is an awful lot like the numerator of the derivative of sine of theta. Yeah, we need a denominator carried along there, which would be this delta theta, right? If that had a delta theta underneath it, that would be, and assuming that in the limit as delta theta goes to 0, that is a definition of the derivative with respect to theta. So let's do that. Let's go ahead and multiply numerator and denominator of this equation with delta theta, and then replace that term or factor there with the derivative of sine theta, which is cosine theta, right? So now this is the one that we multiplied on the numerator. The denominator went into making that derivative, right? And then we carry that along. And just saying that that's approximate there, because that only is truly applying in the limit as delta theta approaches 0. Right? So from our knowledge of Fourier transforms, discrete Fourier transforms, and looking at what is our resolution and across L samples, then in order for us to be able to resolve two targets at two different bearings, then these relationships need to hold, right? So this is our delta. So this comes from FFT concepts, and this is coming from our approximation up here, right? So if we do a little bit of rearranging now, our angle resolution now is the wavelength divided by L, which is the length of the entire array, times or the number in the array, times L, which is the spacing, times the cosine of theta. Now, what's interesting here, take a look at that equation, and now again, this resolution is nonlinear with respect to theta. But we will see here that our best resolution occurs at theta equals 0, right? That's when cosine of theta is equal to 1 at that point, right? And we have this widest unambiguous angle of arrival when L equals lambda over 2, lambda by 2. I didn't actually derive that for you. That's fairly simple. Again, you're looking at the unambiguous range. I do provide some equations for you, but this also rises in antenna arrays and that type of thing. So this is a pretty common spacing criteria, right? So you typically are going to want your elements, your antenna elements spaced at this halfway length spacing. And then we're going to see that our max resolution is going to be approximately equal to 2 divided by L, right? Well, it's not really approximate. It's other than this approximation we made there, but that's going to hold pretty well. And so you can test that for yourself, kind of plug in some values here and solve for everything. But note that this is in radians here. We're need to be careful that we're using the right units, especially when you do the homework assignment, right? Okay, so that now gives us range velocity, and bearing or angle of arrival for multiple targets, right? And we've got some relationships that talk about resolutions for each of those, maximum ranges, and that type of thing. But we achieve some resolution with an array of RX antennas. Okay, so I grab this figure, I just cut and paste it out of Texas Instruments application report. And so since I just did a copy pasta there, we're using their notation in some of these. I don't think it actually shows up in this diagram, but just be aware that some of my notation nomenclature is slightly different. So here's your transmit antenna, and then you have these different receive antennas. Actually, I guess I used omega here. So what if we added a transmit antenna? What if we used two different transmit antennas, right? So here, this isn't strictly MIMO. If you're a communication engineer, you may have seen this before. Multiple input, multiple output, referring to the number of antennas on the input and the output. Your Wi-Fi routers and cell phone systems are often fully MIMO, and where you actually have multiple antennas inside your cell phone or inside your computer, and then on the router box or in a cell phone tower, there's multiple antennas up there also, right? So or it could just be a single input, multiple output, or vice versa, depending upon which direction you're referring to, right? But so here we have one transmit antenna and some number, in this case, 7, 8 different receive antennas, right? Here we're going to add a transmit antenna, but note that with the cost of one transmit antenna, we can get the same number and spacing, if we've done it right here, of received signals from these 4 receive antennas. Here we had, here we had 8 receive antennas and 1 transmit antenna, and we went from 0 to 7 omega. Here we have 2 transmit antennas and 4 receive antennas, but here these are spaced at 4D. Well, in my notation, that would be 4L, whereas these are still spaced at D or L spacings, right? And if you go through the geometry again, looking at how long does it, what are the time spacings of the signals that are arriving here, you will see that there's signals arriving at 0 omega, 2 omega, 3 omega, 4 omega, 5 omega. So we've basically doubled the number of points in the FFT at the cost of a single antenna with proper spacing, or in this case, we've maintained the same number of points in the FFT with half as many receive antennas. So we've got a lot of flexibility. So we can even do 2-dimensional MIMO arrays. So here we have this theta, right? And probably you're looking in it, especially in an autonomous road vehicle, you're really looking at azimuth, right? So if you're facing ahead, then the azimuth direction is a yaw type of angle change from left to right, right to left, clockwise, counterclockwise, but in the plane of the roadway as you're traveling down the road. But what if we wanted some elevation information also. Well, so here you could place some antennas, transmit antennas here, and then another one that's offset from this line, right? So here everything's spaced along a line. But here we've offset this from the line. And now if you go through, again, this kind of equations looking at the incremental path distance relative to each of these and each of these, then you're seeing this type of array. So we're not going to go into it much more, but now you've got some XY or azimuth elevation type information out of this. If you keep going, you could get to maybe some imaging performance, right? So here you're not getting much of an image, right? You might get a line scan out of the thing, but you're not getting any sort of two-dimensional type of imaging. Here we can just start to do it, but it turns out you can cascade some of these chips together and keep increasing the size of these two-dimensional MIMO arrays. And so, all right, so then I'm summarizing some design equations here for you, and I think those are consistent with the notations that I've used in my previous slides. If you downloaded this presentation from last week, I've added this slide, so this is a new slide. Let's look at something here real quick. Yeah, so just to get a little hands-on here, I don't know much about this particular video here, but it shows up in TI's little playlist. And so you see here, there's a distance. We'll probably get some crazy ad here any moment now from YouTube, but we've got a distance along the lateral axis in meters and distance along the longitudinal axis. So this is a distance plot. So this information is coming from your distance, and but that's why you have these kind of circular lines and these radials going out there, because that distance is relative to this point here. And so there's your information. Here's your Doppler range plot. So now you have the range and the Doppler also here. So this is going to be your meters per second type of information. And let's see, this is distance along the longitudinal axis and distance along the height axis. So you're getting a little bit of elevation type information out of that. So yeah, so I think there's another plot, another video that I linked in Moodle that shows, and they're cascading the multiple chips together, and then that's going to give you more imaging capabilities, right? So and PI is not the only one that does this. It's just kind of the one I'm a little bit more familiar with, and I think they've done a good job at explaining how they do things from all that FFT analysis and that type of thing. So here's a number of different selections. TI also has a industrial line, so things are tuned for different distances and distance resolutions, velocities, that type of thing. So you can imagine that a system designed for automotive may not neatly fit into an industrial application and vice versa, right? So they have two different lines there. So, and in your homework assignment, I'm going to have you look at this. Well, you're going to do a design exercise, but then you're going to look at this device and see, hey, does it actually work for this particular application? So here, this is a little bit more your block diagram for the electronics hardware guys and gals. So we have some receive antennas here. We have 4 receive antennas, low noise amplifiers, these mixers to mix the transmitted chirp with the received chirp, right? And then that goes to an IF band. And again, the frequency of the signals coming out there are related to the distance of the targets, right? We do some sampling, then we do a digital front end. This is decimating the samples, filtering them, and that type of thing, right? And then you're going to go out to a coprocessor that's going to actually do your FFTs and whatnot. The kind of key here is a synthesizer and this ramp generator being able to create that linear chirp. You're going to create in this case, a 20 gigahertz synthesizer, and you're going to ramp that over time, and then you're going to do a frequency multiplication by 4. So you're going to get up around 80 gigs. And then that's going to go to some phase shifters to tweak the transmit signals, and then amplify them and transmit them. This multi-chip cascading allows you, and they actually have that registered as trademark, or is that just a note there? I can't read it. So this allows you to synchronize these ramps and the synthesizers across chips. So you're using one ramp, one chirp for all of them, right? So if you're cascading these chips, then you're going to use one of these synthesizers, and it's going to drive all your other chips. Okay, so then here's the data sheet. This is linked, uploaded in your assignment. Let me know if there's any problems retrieving that. But here you see that chip and some antennas. That's probably going to be printed on your circuit board or some tiny ceramics, something like that. But you can calculate out the wavelength, and you find out these are really small, right? But then this is your RF chip, but it's connected to this external microcontroller, and that's doing all those calculations, FFTs and peak searches, and actually going through those equations. And then all that information goes out over some automotive interface. Is that a CAN bus or something? I don't know on this particular one here. So might be a higher speed than CAN. All right, and so then here's the block diagram again, and you'll see that there's, I think, this RF specification on page 21, 8.7 is what you're going to look at. One of the things that I don't mention here is that you have to satisfy a link budget also. Perhaps you looked at this in your applied electromagnetics course, but there's going to be some signal noise issues in order to actually be able to detect those energies in those FFT bends. And as you transmit out, you're transmitting with a certain amount of power. Your antenna is going to have a certain amount of gain, in the direction of interest, and then you're going to, that wavefront is going to spread out in 2 dimensions as it heads out towards a target. It's going to reflect. Not all the energy is going to come back. That's going to be accounted for through the radar cross section, which could be empirically modeled or simulated or something through a finite element analysis or that type of approach. And then as that object is only intersecting a small part of that beam front, and then as that signal reflects back and travels back to the receive antenna, it continues to spread out in 2 dimensions. And so the receive antenna is only intersecting a small part of that. So that's, and the receive antenna has a certain gain also. Then that is going to account for what we call our path loss. So if you look at your gains and your losses, then you're going to end up with some amount of energy at the receive antenna, and then that receiver has a certain noise figure. So 13 dB is not great, but it is at 80 gigahertz, 70, 80 gigahertz. So I shouldn't criticize it, right? So we didn't go through that, but you still, when all is said and done, there's an equation that looks at the maximum distance, and that's related to the chirp time, and that there basically needs to be some overlap of the chirps when it comes back, right? So when the receive chirp has to overlap that transmit chirp, and so we need, and then also I think in this case we're relating that TC to this maximum velocity, which goes back to that phase ambiguity that we might have when we're doing that Doppler FFT, right? So then we're going to have a certain amount of signal, certain amount of noise, and that's also going to limit our range, our maximum range. So we've got to make sure that that's accounted for. Generally, you're going to make sure you have enough power and a low enough noise figure and gains in your antennas that everything's going to work out. All right, so here's the IF bandwidth and some ADC sampling rate. Hopefully, maybe in some DSP course or communication course, there's a concept of Shannon-Nyquist sampling theorem, and we normally say that we've got to sample at twice the rate of the highest frequency in the signal. But actually, if you get fancy about it and you're able to sample both the real component and the imaginary component of a complex signal, then you're really getting 2 data points per sample. And in that case, your sampling rate just has to be at or above the highest frequency in the signal, right? But we're not breaking Shannon-Nyquist theorem here. We're basically taking 2 samples, and we need 2 ADCs, and we need 2 signal paths after down conversion. That one is isolated on the real part of the signal, and the other one's isolated on the imaginary part of the signal. So we have 2 samples for every time that our sample clock ticks, right? So so that's why you're seeing 2 different values here. And Lots of other interesting information here. There's a ramp rate, and I think those frequency range, and that's probably what you need out of the thing. So actually, a frequency range is at the IF or the 20 gigahertz clock, and recall that we multiply that by 4, and this is for the multi-chip synchronization. All right, so let's then kind of finish off with these things. As I mentioned, they're available for automotive, industrial, and defense applications. Some of these same concepts are used in Doppler LiDAR and other type of things. So it's not unique, but very similar type concepts. I think I've mentioned some of this type of stuff. Spectrum is allocated in millimeter wave bands. What happens? How does that aspect impact the design and performance of these systems? So I'll let you think about that a little bit. I know I was doing little quizzes each week of the previous lecture, but I think I looked and people weren't doing them. Maybe I should make a bigger deal about them. But that could be something that you could think about after this lecture and kind of roll that over in your head. How, and particularly as you're going through this homework assignment, you're going to calculate the wavelength and you're just going to plug and chug. But think about it a little bit on how that might affect the design and performance of these systems, and how, if you wanted to do something at a much greater range or lower range or whatnot, how would that impact that? All right, so wow, that was a lot. Okay, well, we've got some time. Let's try to finish this this lecture here. So another big sensor class is cameras, and I'm not going to go as in depth here, but again, get you kind of a starting point. If you are into cameras, imaging, and you want to go down that route, then hopefully I'm giving you some seed information. So used to be our cameras were charge coupled devices, and those were our high performance cameras. But they're kind of expensive. Process engineering that it takes to build those things are expensive, and the sizes and whatnot. So doesn't really fit into consumer products very well, but CMOS does. Everything else is CMOS and a lot of the chips and that type of thing. And so there's just enormous amounts of engineering that goes into making CMOS chips, whatever it's GPUs, CPUs, memory, whatever, right? And so, and then that technology is now in our phones, our cell phones, or before that is our cameras. So all that consumer demand has pushed a ton of engineering into making CMOS as good as what the technology can do, right? So even though maybe the case could be made that CCD technology is kind of inherently better, I'm not going to necessarily say that, but the fact that there's so much engineering effort going into CMOS that it's really catching up and overtaking that. So sensors, these are just some points to keep in mind as you might implement these, right? So these sensors tend to be somewhat sensitive to both visible and infrared light, and you might want one or the other. So you can use filters in front of the lenses if you're really looking for infrared. Those photons are actually absorbed deeper in the silicon, so you kind of need a thicker substrate, a thicker epi layer to be able to capture those photons, and that's just easier to do with CCD technology. So maybe there's still a place for it here and there, just some different trade-offs. We've mentioned a little bit, just covered it a little bit before, about camera depth perception, and that can be done using two cameras, where we can get a disparity map between the two, or we can do that with one camera but take successive photos and actually maybe move in the interim between those different photos, and we can then come up with that disparity where the objects that are close to us appear to move more pixels relative to each of the two images, whether it's coming from two cameras or one camera that's been moved a specific distance. And those objects that are far away are moving fewer pixels in that comparison between those images. And we can even use some relative sizes if you kind of keep track of things. But that's maybe best done with some machine learning type algorithm. That's my opinion. I don't know. All right, so other ways we can get depth perception out of a camera is we could integrate that with a simple LiDAR. Now, Intel's kind of big in this area. They have a whole line of different cameras that provide depth perception. So you can go to the, just search for Intel Sense, I think, cameras. I think that's their branding that they use. And you'll see that they have a few different kinds, but you can do a very simple light or laser ranging type of system. Not so much we're using the LiDAR to image on a whole area and maybe apply a particle filter or something like that, but just to get some range information, right? So you can also do structured light. Now, this is kind of interesting. You can project a striped pattern onto an object, and if that object, let's say, is looks three-dimensional, let's say it's a sphere, then those striped patterns now are going to, when they reflect back to the camera, are going to appear to be bent or wrapped around that object. They're deformed, and you can perceive the shape of that object by analyzing how those lines of this structured light striped pattern are coming back to you, right? And how they're deformed. You know, how easy is that to do? Maybe not super practical in an autonomous vehicle, but it's used in some industrial applications. You can use, let's say, infrared light to avoid interference with the core image, or just try to do it at a frame rate that's not perceptible and you to the human eye, so we're not seeing it, and it can be gated out of any other processing, right? Time gated. But this is kind of slow, power hungry, easily interfered with, whether maliciously or just by consequence. So shutters are another thing you'll see if you're specifying a camera. You need to get one. You're going to see some with rolling shutter and some with global shutter. The rolling shutter is typical of CMOS. And the image is scanned line by line, maybe from top to bottom. If you're imaging a very fast-moving object, or vice versa, you've got a lot of camera shake because it's on a vibrating platform or something like that, then because this image is scanned line by line, that the light image can change while you're scanning it, and you can end up with skewed images, right? But typically you're going to end up with less noise and wider dynamic range. So there's always trade-offs, right? The global shutter, the entire pixel array is sampled at the same time. There's some scalability challenges with high resolution, trying to get all, gigapixels or whatever, megapixels off of a, that pixel array can be difficult, right? And typically more expensive. So some trade-offs there. I think you're seeing more global shutters these days, but yeah, you still may run into that trade-off. All right, so super quick, but here we can talk briefly about ultrasonic sensors. You may be familiar with those little things that can plug into an Arduino board. They're super cheap. They've got two of them, transmit and receive on there. You can have, they're effective over a short range. They're going to have some wide beam width because of, now we're dealing with sound instead of electromagnetic waves. The velocity is a lot slower. The wavelength, therefore, is a lot bigger. So you just physically, you're going to end up with wide beamless. Again, susceptible to interference. These are ad ultrasonics, but there's lots of noise in that regime. But they can be useful for parking and other nearby obstacle alerting applications. Oh, you're about to run over the bike your kid left in the driveway or something like that. And then now finally, LiDAR. Your book goes into this a little bit. So there's a few pages on LiDAR. Less about actually how it's used in terms of that the particle filtering, or how do you actually build up some sort of image using these things, but it does these numbers here I pulled from the book to kind of consolidate it for you. So we're doing light detection and ranging using pulsed light. You can have pulse rates on the order of 150,000 pulses per second. Wavelengths vary depending upon application, how much you want to spend on it. I think this is for aerial type use is 532, is more if you're going to shine laser in seawater in the ocean. Maybe you're trying to do bathymetric measurements, and that would be looking downwards at the seabed and mapping out the heights and valleys of the peaks and valleys on the ocean bed. Do a particle filter on that, and you can kind of localize yourself within that. If you know a priori, have a map of that, or you can do some SLAM, right? So, but this wavelength penetrates through water better than these others do. It's still not great, but it's going to penetrate better. There's issues about whether these are eye safe, different wavelengths, and that type of thing. So, but also amount of energy that could enter your eye. So obviously, we don't all want to be wearing goggles anytime we're close to anyone's car. So we need these things to be eye safe. The thing is has an array of laser transmitters and receivers, and that's able to give you some little bit of azimuth and elevation depending upon the array. So you get a little bit of two-dimensional imaging out there, but to really get more awareness, we're going to rotate that thing. Might be rotated through all 360 degrees. And I think, don't know for sure, but I think those autonomous cars from Waymo and Cruise, the unmanned taxis that are running around San Francisco and a few other towns, are using LiDAR that are rotating, and they're rotating, somewhere on the order of 5 to 20 hertz. It's mechanical, very mechanical type thing. So, yeah, you got to now factor in energy and mostly reliability here when you decide all that. But obviously, there's a refresh rate associated with this. If you're rotating at 5 hertz, you're getting information updated at that rate. Detection, you can do that coherently. That's where now we're measuring not just the magnitude of the signal, but its phase. So it's a coherent detection. With this, we're able to measure phase and extract out Doppler information. And this is ultimately, we get a better signal noise out of this approach. So we don't need as much power to accomplish our imaging task at a certain range, but it is more complex. Incoherent, we're just looking at magnitudes of the signal coming back, and it's cheaper, but is going to suffer higher noise. And then there's the energy. This factors into your iSafe type issues, and so you could go with very high power, long, not just like peak power, but also the duration of the pulse that you're sending out there, right? So it's energy in a pulse would be related to the peak power and the time that's actually on. So you can kind of get around too much energy using micropulse and stuff. Obviously, there's some trade-offs with our detection thresholds and ranges and signal noise ratios and that type of thing versus trying to be safe. All right, so here's a picture from your book. And so there's continuing evolution on these, and I think even maybe the company it's mentioned in your book might have been acquired, but it's an active field of development. But here we have lasers being emitted, and they're in some certain configuration here. And so kind of out on the edges of this system here. And then we've got receivers, right? So these would be electronics are sensitive to that laser light at that wavelength. And they're going to be in these groups. We've got some, arrays here so we can discern this two-dimensional type of imaging, and then when we spin it, we can extend that all around us, right? So, all right, scans an area, builds up what we call a point cloud. So when you do these lasers, the lasers are very, we approximate them as point sources, and so when it comes back, we're keeping track of where that laser was pointing at that instant, right? So we need to encode this rotation of this housing. So we've got to know precisely which direction that was heading. And then we take that 2D array, just like we looked at in the MIMO on the CHIRP radars, or not just like it, but analogous to it, right? So we then build up this point cloud in memory in our processing system. It can be very, very high resolution. We need to calibrate it carefully, right? So this is a physical system here with these spacings, and especially this thing as it's rotating and how it's mounted. Is it really mounted level, that type of thing, right? So distance is maybe a little bit easier to calibrate than bearing or angles, elevation, and that type of thing. So calibration is one of the challenges in engineering challenges in LiDAR. So scanning techniques, trade-off speed, ruggedness, complexity, and whatnot. All right, so there, we're finally finished with lecture 5B, and let's take a 9-minute break. I've got 6:41, 7:41 Eastern time, so let's come back at 7:50, and we'll dive into neural networks and machine learning.